Previously in this series, I've dug into some of the less obvious maths functionality, or I've used familiar things in unusual ways. But this time I want to talk about the mixing section, voltage creation and manipulation, and the summing bus, which is literally the center of this module. So in this video, I want to cover voltage generation, attenuverting, mixing, scaling and offset, the sum, inv, and or outputs, voltage rectification, and along the way I'm going to touch on some interesting uses for the EOC and EOR outputs. But this is the part where maths really lives up to its name. I'm going to be adding voltages together and multiplying by scaling factors. There's no real math background required at all except adding and multiplying, but this is the first time we're going to be really doing that. And as always, the Mordax data is a great tool to have at hand, and I'm going to be using the voltage monitor function a lot, along with the oscilloscope. Getting started, let's talk about voltage generation. A feature that is often forgotten is that maths can just output some voltage for you if you need it. Something that comes up for me a lot is that a module I'm using only has a CV input for a parameter, no physical knob. A good example is the 4ms rotating clock divider. The whole rotate function is pretty important, but at only 4 HP, they had to leave the manual control off. But that's okay, because maths has us covered. Channels 1 and 4 only output voltage if the cycle is running, or if you bring in an input from somewhere else. But channels 2 and 3 will output voltage depending on the attenuverter position. In this example, I'm using channel 3, and that's on purpose. Channels 2 and 3 look identical, but there's a difference. Channel 2 will vary from minus 10 volts to plus 10 volts, but channel 3 only goes from minus 5 to plus 5 volts. Maths doesn't indicate that at all, but the difference can be important depending on how you're using it. In this case, plus or minus 5 volts is even a bit more than I want, but it's the best choice. The whole thing with the rotating clock divider is that you can change up the frequencies of the clock divisions. What used to happen every 2 steps now happens every 3, and what happened only every 8 steps now happens every step. It's a lot of fun when you use it to control drums, because you can go from your regular drum pattern to a break and then back to a slightly different pattern just by changing the voltage going into the rotate on the RCD. One problem point, and maybe it's hard to see in the video, but I'm just making tiny adjustments and I still keep missing the target I'm looking for. That plus or minus 5 volt range is a bit more than I really need. Pretty early in your modular exploration, you're going to run into the word attenuate, which really just means to decrease the intensity of something. If you turn down the volume on the TV, you're attenuating. More commonly, we use it to refer to control voltage, reducing the range of a CV signal. In its most basic form, it's just a simple variable resistor, a potentiometer. A passive attenuator module is dead simple, and it's easy to build if you're at all DIY inclined. You can build one in just a few minutes and it won't even require any power. But there's a limitation. You can only take a signal down from 100% down to 0%. You can't go any louder, and you can't go into the negative by inverting the signal. To do that, you need an op-amp in the circuit, which will allow you to increase or decrease the level of the signal or to invert it. Once you have that, you've got an attenuverter, and each of maths' 4 channels has one. This diagram shows channels 2 and 3, which are the simplest example. We just saw that we can use these as voltage generators. But if you plug a signal into the inputs on the top, you can use those same knobs to attenuvert the incoming signal, allowing it to scale the voltage up to 25% louder than original, or to invert it, flipping the results over into the negative, or into the positive if it was already negative. This does work with audio as well as CV, letting you increase the loudness a bit or to reduce it. You can also invert the signal, although you probably won't notice any difference. The signal is still wiggling as fast as ever, and your ears are receiving the same changes in pressure, so it sounds the same. If you take an audio signal and add it to its inverted version, you're going to hear the volume level drop as destructive interference eliminates some of the signal. Channels 1 and 4 can do the same thing, but you usually want to make sure that you've turned down the rise and fall knobs. Those channels have slew limiters that slow down the transition between voltage levels, so it can alter the signals in a way that you don't expect. I have a separate video about slew limiting and you can learn more there. Another difference is that the attenuverters on channels 1 and 4 will only scale up to the original level. There is no amplification. Channels 2 and 3 can go up to 125%, but channels 1 and 4 are restricted to just 100%. Earlier, when I was controlling the rotating clock divider, I had to make tiny little adjustments because the range of the knobs on channel 3 was too big. That's an easy fix. What I do is to dial in on channel 3 the maximum value I want, then I take the output from 3 and run it into the input on channel 4. Remember that channel 4's attenuators only go to 100%, which means that when the attenuator knob is fully counterclockwise, it's at my maximum value, and then I can dial it down in more fine-grained increments. In red is my channel 3 output, set to about 3 volts. Below that in yellow is the channel 4 output, and you can see that instead of going from -5 to +5, the channel 4 attenuverter now goes from about -3 to +3. Now I'm turning down channel 3, and you can see that channel 4 remains in lockstep with it. Channel 3 is the maximum value, so as it goes down, so does channel 4. So now I've got the range brought down to about -1 to +1 volts, and you can see that I'm getting very precise control. In fact, I can dial in 1/100th of a volt if I ever needed to do that. Maths can do a lot with the individual channels, but it gets really interesting when you start adding those signals together. If it were audio, you'd call it mixing, but with CV they seem to be using the term summing, or more completely, this is the summing bus. We're going to get to that in a couple of minutes, but we'll start with this. Each of those channels can take an input, either CV or audio, and mix them together and send them to the sum output. If you're cycling channels 1 or 4, that'll also be added. The only real limitation is that sum will only output in the range from -10 to +10. So if you were to set channels 2 and 3 fully clockwise, that would be 10 + 5 = 15 volts. But to keep our precious modules safe, make noise maxes out at 10 volts, and everything after that is ignored. Now the first thing a lot of people use the sum output for is to perform a standard scale and offset on CV. Maybe you've got something unipolar that you want to be bipolar, or the other way around. Maybe you want to take some modulation and turn it into a very specific range of voltages to get a specific result. The rotating clock divider from earlier is a good example. Each rotate step is just about 2/3 of a volt, so if you want to stay within 3 steps, you might need to keep your CV between 1.9 and 3.8 volts. But let's look at one of those bipolar to unipolar examples. By now you might recognize the output of the nonlinear circuit's triple sloths. If not, I've got a whole video about it, but the X outputs from it can vary from about -2.5 to +2.5 volts. One thing that I tried to do early on in my modular journey was to control VCAs with it, and I didn't understand why it was just silent most of the time. Now the answer's obvious. You can't open a VCA negatively, it needs positive voltage. What I really needed to do was add some voltage to it so it wouldn't go negative, and then scale it up or down to give it the range that I want. And that's more or less what we're seeing here, with the original in green and the offset one in blue. And here's the opposite case. The EOC and EOR outputs from mass are either 0 or 10 volts, depending on if the voltage is rising or falling. But what if I want it to be -3 and +3, for instance? Well, you can scale it down, and then add a negative voltage offset to pull it down into negative territory. That trick of using the EOC and EOR outputs as voltage sources can lead to some cool effects, and I'm going to cover that in the next video. But now I want to talk about those 3 major outputs from the summing bus: sum, inv for invert, and or. We've already talked about sum, and that's fairly easy to understand. All of the outputs are added together with the caveat that the output is kept in the range of -10 to +10 volts. One thing that isn't obvious, though, is that if you use one of those outputs, maybe you're already using channel 3 for something, then channel 3 won't be included in the sum. This happens if you use any of the main outputs. The sum will only add up the channels that don't have something plugged into them. And I find that I end up doing this a fair bit. If I'm using channel 4 as a clock source, for instance, I don't necessarily want the LFO cycling up and down and being added to the sum. Now you can try to get the attenuverter set to exactly 0, but it can be finicky and dialing it in is pretty tough. And if you accidentally nudge it while you're playing, it can be jarring. Similarly, if I'm not using channels 2 or 3, I don't want that offset voltage added in. My solution for this, and you may have seen it in some of the videos already, is to use a dead plug, at least that's what I call them. I've sacrificed a patch cable, cut off the jacks, and when I want to take a channel out of the mix, I plug one of these in instead. You can always just use a patch cable and leave the other end unplugged, but I don't like having it flapping around like that. But while we're on the topic of taking things out of the sum, it's important to note that the unity outputs from channel 1 and 4, those are the ones notated with a little integral symbol, they're not part of the summing bus. They're basically just pass-throughs for the inputs into channels 1 and 4. There's no attenuation applied, and it just takes the input voltage, or the cycling LFO value, and outputs it at 100% strength. They're not added or removed from the sum, so you can use them for different things. One thing that I do fairly often is that I might want to take channel 1 cycling as an LFO and use it as two different voltage levels. I can take the regular output, attenuate it where I want it, and use it somewhere, and then I can take the unity output, put it back into channel 2, and attenuate it to another level to add it to the sum or use it on its own. But there's two other outputs on the summing bus. One is in for invert, and it's pretty easy. It's just the inverted signal that's coming out of the sum. If the sum is varying between 2 and 4 volts, then inv is going to be varying between -2 and -4 volts. The other one is OR. Now OR is an odd one, especially if you come from a computer background and you're used to the idea of binary logic. There's only two possible values, 0 and 1, on and off. The output of an OR gate will be high if either of the inputs is high. So if you send in 0 and 0, you'll get 0 out. If you send in 0 and 1, you'll get out a 1. Send in 1 and 0, also 1. And of course, if you send in two 1s, then you're going to get a 1 out. And we can see it's the same thing if we take three inputs and OR them. As long as any of A, B, and C is 1, then the output is going to be 1. And the same with 4 inputs. And you're probably seeing the pattern now. There's only one way to get 0 out, and that's if nothing but zeros come in. But this isn't binary, this is all analog, so how does that work? Well, it's a bit counterintuitive, but it works by returning the voltage of the highest output. Out of all the 4 outputs, what is the highest, and output that. But that's kind of weird, right? How does picking the largest voltage equate to the concept of A or B? A good place to start looking is just to consider the outputs of 0 and 1 as 0 volts and 1 volt. And just like with binary, if you put in all 0 volts, the largest is 0, so that's what it outputs. If we put in 0 volts on 3 of the inputs and 1 volt on the other, the largest is 1 volt, so it outputs 1 volt. If you put in 0 on 2 inputs and 1 volt on the other 2, the largest is still 1 volt, and so on. But of course we're not limited to zeros and ones. So what happens if we send in 3 volt, 0 volt, 1 volt, and 1 volt? Well, then the largest is 3 volts, and OR outputs 3 volts. If we put in 4, 2, 0, and 8, well then it's going to output the 8 volts. So far I've concentrated on sort of treating it like an OR gate, but there are some neat tricks we can do now that we know that it's actually a max output. So I'm going to fire up channels 1 and 4 cycling as LFOs. Channel 1 in green is going pretty fast. Now add channel 4 in red, and it's running slower. And you can see that with the green oscillating quicker, it leaves lots of time where the red trace is actually higher. Now I'm going to turn on the yellow trace, which is the output from OR. It's pretty much invisible, which makes sense, because OR will always be the value of one of the outputs, so the trace is always going to be exactly on top of one of the others. So I'll adjust it down so that we can see the yellow trace now below the other two. And yeah, we've got this jerky, irregular pattern. Well, it's almost a pattern. When channel 1 is higher, it outputs that. When channel 4 is higher, it outputs that instead. What I like about this is that the outputs from channel 1 and 4 are tightly related to the OR output. So when you send them to different modules, the modulation is all related. It also makes a good destructive audio mixer. You can run in multiple audio signals, and since it's just grabbing whatever is louded in that fraction of a second, it all gets munged together pretty nicely. One quirk that's definitely worth remembering is that this only works for positive voltages. If you send in a negative voltage, it gets treated as 0. That's a bit odd, but it's useful behavior that we're going to use next. So one last topic, voltage rectification. We saw earlier how we can use scale and offset to make a bipolar signal and shift it up to make it positive. This is another way of doing that. Voltage rectification basically just says how it's going to handle negative voltages. It comes in two flavors, half wave and full wave. Half-wave rectification simply gets rid of anything below 0. And that might remind you of what we were just doing with OR. It literally cuts off anything negative and returns 0. So that's pretty easy. Just make sure that the other channels are zeroed out or plug something into channel 3's output so it doesn't get included in the bus. That leaves a bunch of times where things are 0, and that might be something that you want. It makes for interesting modulation. The other version is full wave rectification, and it kind of flips the negative back over into positive again. In math, this would be the absolute value of the voltage. This patch is a bit tricky, but it's a clever use of the OR/max feature. We put the same signal into both channels 2 and 3. We turn the attenuator for channel 2 to about 3 o'clock, and for channel 3 to about 9 o'clock. It's the same signal going in, but one channel will be left normal, and the other will be inverted. So there's always going to be one positive signal and one negative signal, and OR will only output the positive one. Pretty cool. Wow, we really covered a lot of ground in this video, and there were a lot of numbers flying around, so I've put together this cheat sheet with all the specifics. It's not really that hard once you know that there are differences, but this can help you while you're figuring it out. This and the rest of the slides are available at the link below and in the description. And that's it for this video. Thanks for watching, and if you stuck around this long, maybe consider subscribing. That's what all the attractive people are doing.